All right, I'm going to do two topics as I have in the description there tonight. First one is going to be on the upcoming solar eclipse. And let me go and turn off the volume there. There we go, so I don't get an echo. And let me get a drawing out that I made in Inkscape. And this is some text also with it, but this is the best I could do to try to illustrate why the usual depictions of what happens during a solar eclipse are probably misleading at best, and to see if I can explain some things. Some of the terminology we have, you can see here that we got on the right, we have the sun, and they depict it as larger than the moon. This is, of course, not to scale or distance or anything. And they will draw lines from the tangent line that goes across the outer edges of the two bodies, and tangent lines that go from the bottom of one to the top of the other. Now, why do they do that? Well, the thing is that, first of all, a tangent is just what you see there. It's a line, a straight line that touches the outer edge of a circle or sphere at one point. And what they're doing by drawing those lines is finding the areas of the darkest part of the shadow, the umbra, and the so-called blurrier parts of the shadow, the edges, which is the penumbra. And they're finding these by looking at the difference in the two tangents. So once again, you can see that there's a tangent that goes on the outer edges between the two objects, and one that set that goes from the top of one to the bottom of the other. And what these do is show visually how any given shadow with one light source will behave on the other side of the object being lit. And you can see there that the relative sizes and the distance between there's three things here. The one is the sun, the second is the moon, and the third, of course, is where the shadow lands. I probably should have drawn something here to say that this is a surface that the shadow is hitting. That distance to the inner edge, I guess you'd call it the object edge of the first body, and then there's a distance between that outer edge and the inner edge of the light source, and the relative sizes of these things. Those all are factors in determining the size of the shadow, the total size of the shadow, which is the penumbra, and the dark inner part where there isn't any light, given a single light source. Okay, so that's pretty much what I'm saying here, is that the penumbra is where you will see at least a partial eclipse, and the umbra is where you'll see a total eclipse. And the shadow size is determined by the relative size of the light source and object, and the distances between them, and also the observer's position in the shadow, which is this edge. In spite of the moon's or the sun's alleged size, its distance is such that it is essentially the same as that of the moon. In other words, from our perspective, the sun and the moon look the same size. So by the time the light of the sun reaches us, and given the alleged distance of the current standard model, the distance from the moon to the Earth is negligible, then we can, for the purposes of finding out the shadow size, consider the sun as the same size as the moon, or maybe slightly larger and a little bit behind. We know it has to be behind the moon a little bit in order for the moon to pass in front of it if the moon is causing the eclipse. So for all practical purposes in the standard model, we can consider the sun to be the same size as the moon and some distance, short distance behind it. So if you look up the term point source, there's some confusion. I've heard people talk about point source. The issue is that there are no other lights coming from other angles. There is only one source of light, and that's what they'll use in physics. And that's what matters, because we can all agree that there's not going to be light sources coming from other angles or other sources beside the sun, because light from the stars is really not lighting up the Earth. It's just points of light we can see in the sky. They, if the moon weren't there at night, you could see the stars, but those stars would not provide you any light on the ground for the most part. So at any rate, that's what a point source is. It's a single source of light, okay? And as I said, because of its alleged distance and alleged size, we can consider them the same, which is why I have on the bottom drawing here, I'm pretty sure you can see, well, I don't know if you can see those here yet. It's a little bit delay on the public watch page, but okay, there we go. The bottom illustration is the one that I think is more accurate to the standard model. If they were going to draw a physics of light drawing to show what the standard model would predict, this is probably more accurate on the bottom here. Shadow size determined by the relative size, as I said, and the distances, and we have a point source. There's no other sources of light but the sun. Now, some people will say that the sun is a point source because it's evenly lit all over, that there's no brighter and darker spots, but that's not entirely true. I've looked at the sun through filters, and it does definitely look brighter as you go toward the center. The edges are darker, and we can't blame that on the filter. I've looked through many different optical devices and put different filters on them. They all do the same thing. So I think it's safe to say that even with a point light source, you're going to have a bright point at the center, but it won't be as bright at the edge of whatever size light you have. It just won't be. But it's a point source for the purposes of physics illustration. And so since the sun, for whatever size and distance you want to give it, by the time it gets to Earth, it is the same size as the moon pretty much. Then the second drawing is the one that's probably more accurate. There's still a penumbra, but it's a lot smaller. And the important thing is the size of the umbra. In this one, the umbra gets smaller than the moon. And this one, it stays the same at best. It would only get bigger. What the penumbra is the blurry edge, so to speak. So, or partial eclipse that you would see from this perspective, looking out toward the moon and the sun, you would see a partial eclipse in the penumbra areas and a full eclipse here in the umbra. And I think for the purposes of trying to determine the distance of the sun and moon, you're going to be probably looking at the whole shadow, not just which parts of it are dark and which are lighter, because even if you can see a little bit of the sun, I think it would be safer to say if you see any bit of eclipse at all, you're in the shadow diameter to some extent or another. And that would be a better measurement of the size of the shadow, because measuring where the umbra and penumbra line is not going to be real easy to do from the Earth because of the size we're talking about. So anyway, I think this illustration is more accurate. We still have tangent lines to the tops of each and the bottoms of each. That's determining the umbra. And we also have these top to bottom tangents that determine the penumbra, because that's just the nature of light. It's going to spread out even from a single point, because you can't guarantee that all rays of light are going to be parallel just at this diameter. It's going to spread out as it travels. It just does. So if we know the shadow size, we're at this end, so we should be able to measure it. Given the sizes, though, it's going to be, the difficulty comes in our size as people relative to the size of the shadow. And you would have to have people just at the edge where any bit of the eclipse can be seen, and find, all around in a circle, basically, people who are just barely able to see it. That would be the edge of your shadow. So if we know the shadow size, we can determine the distance from Earth to the sun if we know or presume the distance between the sun and the moon. We can make a good estimate of that distance by presuming that at least one sun-moon diameter distance is required in order for the sun to pass behind the moon. We can also use this method to see if the standard model is correct given the presumed sizes and distances of the sun, moon, and Earth. They're supposedly about 239,000 miles, which is 30 Earth diameters, thereabouts. Close enough for this exercise. So you have 30 Earth diameters between the Earth and the moon, and 93 million miles, or 11,730 Earth diameters from Earth to Sun. That's where the scale, modeling this to scale comes in, if you presume the sun is large and far away. But as I said, let me scroll down here to the next paragraph. In any case, the moon's shadow, even just the umbra, should never be smaller than the moon, since the sun and moon have little angular difference in diameter from the perspective of Earth. That is to say, they both look the same size from here. So there's little angular difference. Okay, so the shadow should not be smaller. Even the umbra, the darkest full eclipsed part, should not be smaller than the moon. So that means, since if the moon is 1/4 size of the Earth, then the shadow should take up 1/4 of the Earth. That just seems logical to me. So looking again at that paragraph, I pulled out a reference that gives some calculations. I'm not going to go chug through the math. But here's a link to an animation. Let me put that in the chat. Let me get rid of that dot at the end. You don't want that. Copy and paste that in the chat. And that is an animation of lights and shadow. And I don't want to, push my luck with bandwidth and crashing and stuff to show you that, but so you can go see that later. And the only other thing I really had to say about the whole eclipse thing is that, as a side note regarding the distance to the moon, consider the issue of being able to zoom in on it with optics, cameras, telescopes, whatever. If it were 250,000 miles away, no amateur optical instruments would show a significant difference in object size at maximum zoom. So in other words, if you're going to zoom in on something that's 250,000 miles away, your camera or scope isn't going to make it that much bigger, especially something that's 1/4 of the size of the Earth. Yet we can zoom easily on the moon, even with a cheap camera, and its diameter changes very obviously. So it can't be that far away, given the size they tell us it is. It just can't be. So I think it's safe to say that the standard model is wrong, at least in that regard. And if it's wrong in that regard, then everything else has to be recalculated, because we're dealing with things that, if we know, like I said, if we know this shadow diameter, we can figure out, if they tell us the moon is a certain size, what the distance is. And that, because it doesn't matter how big and far away the sun is, what matters is what it looks like compared to the moon from our perspective at this end of the shadow where it's hitting. Then, assuming that a moon is a certain size, then the apparent size of the sun is the same, and it's not going to be very far behind the moon, because, like I said, they look the same size to us, so it can't be very far behind it. Now, another thing that I didn't bring up before was that you've seen on all the animations or images of the path of the solar eclipse, it goes west to east. And that'll be easily verified. That's probably accurate, where you're going to see the total eclipse and at what time and for how long. Those things are fairly accurate, and we can easily check those along, people living at various points along the path. But the problem is that in order for a shadow to move the opposite way that the shadow-making object is, the only way I can think of you can do that is to move the light. You can't get that by spinning the Earth. That is to say, if you're sitting on this side and you want the shadow to go one way and the moon in this illustration to go the other, which it has to be if the shadow is going west to east and the moon is going east to west, as we know it does, then the only way to make that happen is to move the sun, not spin the Earth. Because no matter what you do with this surface where the shadow's hitting, the angle of the shadow won't change if these two things aren't moving. And even if the sun is moving, from our perspective, they're saying, the standard model is saying, for all practical purposes, it's only our spin and the fact that the the way we spin makes the sun appear to move faster, is why we're getting this eclipse that only lasts a couple of hours. But here again, the shadow can't move the opposite way. It would follow the moon across the United States, east to west, if it were all due to the spin of the Earth. Okay, you can't get the shadow to move the opposite way unless this light moves. Okay, the spin of the Earth has nothing to do with that. All it could possibly do is we have the moon and the sun moving, but they're moving in the same direction at different speeds. So I don't know, I haven't really done an experiment to see if the shadow does move opposite ways if you move mainly only one of those objects. Regardless of if you don't have any spin where your shadow's hitting, to move this object, if you had a ball and a flashlight and you don't move the flashlight but you do move the ball, I don't think we're going to see the same kind of long path of the shadow. It might move a little, but I don't think we're going to see what they're telling us on the maps is going to happen if it's mostly due to this Earth's spin. That's just how I see it anyway. But yeah, I probably should have put that in the title, looking at chat there. Anyway, it'd be nice to hear anybody who might watch this video later or anybody in the chat right now to see if you think this is accurate. This was something kind of off the top of my head that I did yesterday. I did this drawing. This is Inkscape. This model came from, I actually pasted in one that I found from a NASA site, and it was really low quality. So I remade it in here and I erased the original. So I drew all these things and put the text in. They didn't have any text on theirs. And drew the tangent lines and the umbra and penumbra and everything. And then I resized the sun to be exactly the same as the moon, drew my tangent lines and everything. So this is my drawing, and the facts that I look up on distance were from standard NASA sites, standard cosmology sources, some from universities and whatnot, not all wiki stuff. So you can look up the definition of point source. You can look up the distances for all practical purposes. When we're talking about this kind of scale, we don't need to have exact inches or any millimeters or anything like that. I think saying that there's a certain number of Earths between the Earth and the sun, for example, is good enough for seeing if the model even works at all. Okay, and like I said, there's supposedly about 30 Earths between Earth and the moon, and 11,730 Earths between the Earth and the sun. So huge distance difference between us and the moon and the sun, of course, on the standard model. But like I said, it doesn't even matter, because by the time, from our perspective, us being the end of the shadow, where shadow hits, we don't care how big and far away the sun is. All we care about is its relative size, appearance-wise, to the moon, and how such a light would make a shadow. You could probably do an experiment if you don't have a light, like I have different size rubber balls here. That one is I have that's about 4 times the size of another ball, and I can't make the shadow do anything close to what they're showing on those maps. But as far as the light goes, I don't have exactly the size light I need that's the same size as the moon in this experiment. So what you could do, which I haven't done yet, is to get a piece of cardboard and cut out a hole the size of the moon, whatever, whatever scale little rubber ball you have, make that the moon. Cut out some cardboard, put it here, put it here really, make it the same size as the moon ball, and then shine your light that's bigger than this hole, and only the light that's the exact size of the moon will get through there. It will make a nice straight line, and then you can check the size of the shadow and calculate your distances, and then try moving various objects in the scenario to see if you can duplicate the west to east shadow. So here again, these two objects are moving east to west. from our shadow perspective. And the question is whether anything but just moving this will get you a shadow that moves west to east. So that'd be a good experiment to do. Maybe I'll get to try that sometime, maybe tomorrow. But here again, like I said, how can the moon be that far, even, regardless of the sun's distance? How can the moon be as far away as it is? I can zoom on the sun too. With the filter on, you can see, and it's interesting that with the P900 camera, it has an automatic mode called moon mode. And what it does is you turn on the camera, set the mode, and you center the moon in the middle of the viewfinder and just press OK. And it zooms and focuses and puts the moon right nicely in the middle of the frame. And, compensating for the light of the moon is supposedly, if you have a full moon, it works on any of the phases too, but best on a full moon, it will change the aperture to get you the right exposure so the moon isn't all, blown out because of the high contrast with the night sky. But what's interesting about that is that doing that same thing, the camera doesn't know what it's looking at. It only knows that the moon, it presumes, is a certain size and distance away, and that it knows how to focus, set the optics to that distance. But you can use that on the sun with your sun filter. If you point at the sun like you were doing with the moon and press OK, the sun winds up being the same size in the viewfinder that the moon was, which shouldn't be a surprise since we know that they both appeared at the same size in the sky when, anyway. But the fact that the camera sees them the same, when it comes to zooming on an object, it presumes to be a certain distance away and a certain size, as would be done with the moon, then what does that say about the sun? The camera doesn't know the difference, and it gets the same result with both. You get the same size object. Scientist in a white lab coat, and I borrowed this from my very tall son, and so my sleeves are hanging off my hands and all that. But I got me a really nice bright flashlight and a rubber ball and a shadow. So the thing is, we're told that the sun does not move, and that the moon is going past the sun. And it's going to be hard for me to look at you guys and look at this at the same time, but hopefully you can see. I just want to make sure that's on camera, that if you move, this is the moon, okay, this ball I'm holding, this is the moon. And if it's going this way across, say that chart on the wall is a US map, okay, it comes in the east and goes west, okay, which way is the shadow going? East to west. So that cannot explain the actual observed fact of the moon's alleged eclipse shadow going the opposite way. The only way you can do that is to move the light. See, when you move the light, the shadow goes the opposite way, because if, say, the moon is starting in the east, moving west, the only way you can get the shadow to go the other way is if it's changing in relationship to the light. So if the moon is going this way and the shadow is going that way, the only way to do that is to change between these two lights, and they tell us the sun's not moving, okay? But if the light doesn't move, the shadow goes the same way as the ball. It goes the same way as the moon. The only way you can do that is to make the moon the pivot point of this. Say there's a line between the sun here, the flashlight, and the ball here was just the moon. If you think of the moon as a pivot point between the line from the light to the moon to the shadow on the wall, see, the moon is pivoting, is where it pivots, okay? If you draw an imaginary line between the shadow and the flashlight, the moon is where it pivots, okay? That's the only way you can get a shadow go the opposite direction from east to west. It can only go west to east if the light's moving. Okay, and they tell us that the sun appears to move. It isn't really moving, but it appears to move. But it only appears to move because the Earth is spinning. But I don't care how much you spin that wall, that poster back there, a shadow is not going to go the opposite way the moon is going. It's just not. It's just the whole thing is going to travel. Moving the wall would be the same thing as these two things, the sun and the moon holding still and the earth back there, the wall spinning. I can do the same thing by moving the earth and the sun, or the moon and the sun together. We still don't have an opposite moving shadow. We have a same way moving shadow. So there's only one way to make the shadow go the opposite way, and that's to move the light. Okay, so if in the standard model, the moon here is throwing the shadow because it's in front of the sun, then the sun must be moving. There's no other way to explain that. And, white lab coat, I must be a scientist, therefore it must be.
Just a quick little hangout about a picture of the moon that I've had, one that I took last summer that I've had as my desktop background. I was just looking at that and going, you know what? There's this question of the moon's shape. And the question is it a ball, a sphere? Or is it a flat disk? Or is it a concave dish? And aside from actually going there and looking and getting outside of our atmosphere, we know enough about optics and cameras and telescopes and light, the physics of light, to tell us, at least rule out some things. One is, look at how sharp the foreground focus is. And my machine is quite laggy. I'm trying to look into ways of improving that, but I have my mouse running down here at the lower left at this ridge. I believe those are the Appian Mountains or something like that, named after some place in Italy, I understand. Nice sharp edges on things for the most part. That's where I was focused. If you get out toward the edge, things get blurrier. Okay, it might not be as obvious on the watch page video there, but it is on my screen, and this is somewhat blown up. On the original size is quite large, so this was a smaller picture in my picture viewer to begin with, so I blew it up a little bit just so you can see the difference, and it's still probably hard to see, but it's nice and sharp right here by this mountain range, and it gets blurrier as you get away. What does that tell you? If you know anything about light, or especially photography, you know something called depth of field. The more you zoom on something, whether it's macro or micro, the shallower the depth of field, meaning a narrower range at which the distance will be in focus. Okay, the objective, whatever you're looking at. For example, if you want to take a macro picture of a flower and you want the background to be blurred out, you can do that in post-processing, but you can also do it right there when you take a picture by using a macro lens, focusing at a very short distance. That will cause everything around the center where you're focusing to be blurry. And that's a shallow depth of field. And the same thing is true at the other end of the zoom scale where you're going far away. And that's the case with the moon. Of course, with the P900, that even that with the 83 times zoom was not at its maximum zoom when I take pictures of the moon. It is a little bit short of that, but not infinity. At infinity, pretty much everything is the same focus. The depth of field is pretty deep because you're not tightly zoomed. But if you do zoom in, as I did for just a part of the moon rather than the whole sky, if you shoot infinity, you generally aren't zoomed. If your focus is in infinity, if you have, a couple other different settings on your camera. But if you zoom in on something tight, like I said, it's going to be a narrow depth of field. Okay, but even at infinity, that still doesn't mean, if I might have said that in a confusing way before, infinity doesn't mean everything's the same focus. It just means how far you're zoomed. So I might have got ahead of myself there. Sorry about that. So this is where I was focused, more in the middle, because part of the picture is off the screen here. And then as you get toward the end, sorry about those artifacts on my cursor. That's a problem I'm having with my computer. It gets blurry. Okay. And that blurriness is telling me that the moon is not flat. Okay? If you zoom real tight on something and the center of it's sharp and the edges are not, they're at a different distance. That's what I'm trying to say with all that bit about depth of field. It's a different distance. Now then so we can rule out the moon being a flat disk. But is it curving away or curving toward? The problem with curving toward, that is to say a dish or concave moon, is that you would expect the opposite side of the moon to be lit. In other words, since the sun allegedly, if the sun is lighting the moon, we don't know that for sure, but if something, we can see that the light is coming from the right to the left because of these shadows on all the craters in the mountain range and everything. All the shadows are on the side where the light's coming from, and the opposite ridge is lighter. That's what light does. If you take a golf ball or some other irregular surface on a ball and shine a flashlight on it, you will see the same thing. You will see shadows on the side toward the light, where the light is coming from, and the opposite side of these indentations or raised up portions like this mountain range. An indented one will have the brighter side on the opposite edge because the light is not hitting in here and it is hitting that edge. With these things, they're up, and so they're blocking the light, so they have a shadow on the opposite side. Everybody knows that's how light works. Okay, so the light is coming from the right side of the picture to the left. Okay, if that's the case, whatever the source of the light, it's coming from the right. If the moon were a dish, then this side would be dark, just as this, think of this as a mini model of a dish. I mean, it's indented, right? When light comes from this side, the side the light's coming from is dark. The other side is light. But because we also on the moon have these raised portions, we know that the light must be coming from this side, from the right. If it were a dish, it would be lit up on the left side. Okay. So because we have both indentations and raised up portions, and they're all consistent with light coming from the right, then if this were a dish, the brightest portion would be on the left side, but it isn't. So I am forced by the laws of physics and the known properties of light, the observable properties of light, to say that the moon is a sphere. Okay, this is just science. This is not what I want the moon to be. I don't care. I want to know the truth, whatever it is. Now, of course, this doesn't mean anything about any other shapes of any other objects, especially the Earth we're standing on. Because you can't look at the sky and figure out what shape the Earth is. So all I'm saying is that the moon appears to be, because of this photo and many others, appears to be a sphere. Whether it's solid or not, whether it's real or not, whether it has strange properties of refraction and reflection, those are different questions. The point I'm making is that because of the way the light looks in this photo and the fact that we have a depth of field, and that by both the indentations in the craters and the raised up portions of these mountain ranges, we have a consistent right-hand light source telling us that this is not, the whole thing is not a dish. It's not concave. It is convex. It's a ball, a sphere. This is the moon only. Okay. Other objects in the sky, I can't say. There is no depth to speak of on the sun, unless you consider the fact that the center portion is brighter than the edges. I've seen this myself with solar filters on my camera and or telescope. So it too could appear to be spherical. Here again, it's very unlikely that it's a dish, a concave thing. The rest of the sky bodies, the points of lights that are stars and the alleged planets, which means from a Greek word that means wanderer, they are the wandering stars, the stars that move and don't stay in constellations. Those would be what we call the planets, but they are pretty hard to get depth out of those. And here again, we don't know by optics alone whether they're small and near or large and far away. We cannot tell. We don't have enough hard data. But what I am saying, though, on this quick little hangout is that because of the sharp focus toward the center of the photo, the blurriness at the edge, we know the moon has depth. And because of both the raised mountain ranges shadows and the indented crater shadows and the light on the opposite side, we know the light in this picture is coming from the right, going to the left, and therefore it cannot be a concave dish. So I have to say, all things considered, that the moon must be spherical. Whatever else it is, I don't know. And what anything else is, I don't know. I'm just saying this about the moon. So I guess that's really all I had to say today. Mostly I'm going to be on Steemit and DTube. I'm moving over to that. I'll leave this stuff up. And I'm doing this video here because I really just got started with DTube and Steemit. So I thought I would put this here, and maybe someday I'll put it on Steemit. I don't know, but I'm thinking I'm not going to put Hangouts on another platform. That just kind of doesn't seem to fit. Anyway, put in comments later about what you think of the rationale that I'm using here on optics and light and all the properties of the whole photo. I guess I could, let me see, unzoom this somewhat so you can see there's the whole picture. You can see also the dark part. In some photos, it looks for all the world like there's just nothing there. And if you enhance the photo in Photoshop or GIMP or something, it still looks like there's nothing there. But you can see, you can follow this range, follow the artifacts on my silly mouse. It still continues into the dark here because there are higher portions that a bit of the light can hit. Okay. Same over here is a little bit of a crater, some little spots here. I don't know if you can see on the screen. And so clearly the moon, these other portions in the dark are there. The moon isn't disappearing. Okay. And so here again, this was more the center of focus. And I might add that if you use the automatic moon setting on the P900, it is very sharp in the center. It's meant to be sharp in the center. And the whole moon will look sharp if you have the whole moon in your viewfinder, which is what the moon setting does. But then what I do is zoom in after it sets that. Okay, so it's not changing its focus when I zoom in. Okay, so it did its, let me see if I can get rid of some of those. I guess I can't. When I did the automatic moon setting, it sets for the moon filling the frame, and the whole thing is in focus then. So this part in the center is what it's going to be weighted on, and it's nice and sharp. But then, like I said, if you zoom in, this is only a small portion of its actual size. And then I move up like this. We can see that these portions are nice and sharp still. That edge is not. And these things look, these circles get more elliptical as you go toward the edge. That's typical of if you draw a circle on the surface of the moon or on the surface of a ball, and turn the ball away from you so that the circle is toward the edge, it's going to look more elliptical. That's what it does. So once again, if you just got here, I'm talking about depth of field in this photo that I took last summer, and the fact that on the automatic moon settings on the P900, you get the whole moon in the frame and the whole thing is sharp. And then I zoomed in when I took the picture. After it made those settings, I zoomed some more, which does not change the focus. And the center, these parts here, which are more toward the center, let me back out again and show you where things are. Like I said, when the P900 focused, it focused on the whole moon, and it's weighted toward the center. So this stuff is going to be nice and sharp, it's more toward the middle. Okay. But then I manually zoomed in, not on manual settings, but you can change the zoom even after it picks the moon scene setting. Okay, and I didn't change anything but the magnification. And then now, this is a small portion of, that's the whole picture, but it's smaller because it's fitting in my picture viewer. Well, now if I zoom in a bit, I still don't think I'm at 100%. That's when I was showing you this picture and how these things, by their properties, are showing you the light's coming from the right. And because we have both raised mountain ranges and indented craters, it's consistent with light coming from the right. And because it's brighter on the side where the light's coming from, it is not a disk. It's not concave, it is convex. And as you go away from here, things get blurrier, which means the moon has depth. That's depth of field. And we're very zoomed in, not to infinity, but very zoomed in. And therefore, you have a shallow depth of field. I think I can still zoom in some more. And I have to be careful to use the scroll bars instead of just the mouse wheel, because otherwise it will try to go to the next picture. And then it gets a little blurry. You zoom in too much, it's going to get blurrier anyway, but it's not as blurry as the edge. So that's the point there. Also, while I've got this zoomed in, see the raised dot, raised dot, raised dot in the middle. That's a lot to do with, this is something that can be duplicated in a lab regarding electrical arcing, and especially in a plasma field, I understand. And these are all very shallow, especially for their size. They are not impact craters at all. I don't think any of them are impact craters. And they are not, there's no debris, there's no pit in the middle or anything like that. And so these probably happened when the moon formed, or as the aftermath of the Great Flood. A lot of things went bad during that time. So we can't say why the moon has the features it does. Well, we also know that some parts are much more reflective than others. You can't say there's suddenly a big spot that isn't as well lit. The light goes gradually to dark. And so therefore, this is more reflective, whatever this stuff is. More like snow almost, and this being like a black ice lake, black ice being transparent ice. And you can also see a streak that goes all the way across the frame here. Okay, it's always there on the moon. And by the way, I have pictures of an astronomy book from the 60s that show the moon's features essentially what they are today, maybe a slightly less resolution, but there they are. So the moon has not changed at least since the 60s. And we have things like these streaks that go as far as it could be going past the rim there around the edge. And there are other streaks too on the Tycho crater and the Copernican crater on the other opposite corner, also have long streaks on them. And so, and we have some streaks here. This could indicate arcing. It could indicate, I'm going to say just, how it formed, because certain materials will bubble like this, bubble and pop. These look more like popped bubbles, a lot of them. They're certainly not impact craters. Question in the chat, or a statement in the chat about the P900 moon settings. I don't think they're trying to hide anything, because what I did this last summer also looking at the sun is I used the moon setting. For all the P900 knew, I was looking at the moon, okay? But I pointed it at the sun instead and got the same result as far as the size of the sun, maybe slightly different, but not much. The whole sun fits in the frame. It thinks it's looking at the moon. Okay, so, and it's nicely sharp and focused around the edges. Of course, there's not much in the middle to focus on, except if there are spots. And I've done that too. You can see on my Cosmology playlist, which I will add this to. And so the problem is that the P900, although it is programmed, I can also cross-check it with my telescope. Okay, which is purely optical. I bought it decades ago. And there's nothing electronic in it except the motorized mount, which doesn't know where it is until you tell it, because even if you use the motorized mount to track things, you still have to point it true north, which is toward Polaris. B, make sure it's absolutely level. And then C, line it up with 2 known fixed bright stars in the sky. Okay. If you don't do those things, it will not track what you're looking for. So it doesn't have any magic in it telling you, putting stuff on the frames that isn't there, putting fake images in the frame. It's just not doing it. The telescope is purely optical, and its electronics are not that smart. Okay. Otherwise, I wouldn't have had so much difficulty using the thing to track objects, to find them and track them. So I can compare those results with the P900, and they are identical. So the P900, in my opinion, is not doing anything to fool anybody or hide anything, because it doesn't know where you're looking. Okay. And I can guarantee you, if you take apart the scope, you will find no electronics in there. And if you think there's something there that is too small to see or is well hidden, that is an argument from silence, and it is something you would have to prove. You would have the burden of proof for. Until I see such evidence in my telescope, I'm not going to entertain the idea that there's something fishy going on. But because you can make your own telescope. You can get some lenses, you can grind them yourself if you're that paranoid, and make your own telescope. Okay, there's plenty of instructions how to do that. And yes, it is purely optical. If you especially get your own grind your own lenses, there are books on how to do that. You will get the same results. You can put, an ordinary magnifying glass, a set of them from your house, take them out of their little holders and put them in a cardboard tube, if you know what you're doing with the distance and the shape of the lenses, and make your own telescope, and you'll get the same results. And so this is no trickery that I'm aware of. The charge of trickery needs to be proved by those who make it. And in my opinion, as I've said, I've compared what the P900 sees with what my telescope sees, and not just one telescope. I have others that aren't as high magnification, but they tell me the same thing. There's nothing fishy going on. And like I said, the P900 doesn't know what I'm looking at. It only knows what setting I chose. It doesn't know if I'm looking at the moon or the sun or the stars or a mountain range in the distance or anything like that. It doesn't know what I'm looking at. If it did, it would track things for me, which would be awfully nice, but it doesn't do that. You have to buy a separate motorized mount to track things for you. And even then, you still have to set the thing north and level. And because if you don't do that, if you just set it on a table and tell it track my stuff, it won't be able to do it, because it doesn't know where you are. It doesn't know which way you're pointed. It doesn't know what you're looking for, because you don't say, find me the moon. You just say, here, it just has settings that say these are optimum for putting the moon in the whole frame. That's all it knows. Like I said, I proved this by looking at the sun with it. It didn't have to change a thing. So as far as it's concerned, the sun and the moon are the same distance, because it doesn't know I'm looking at the sun. And yet the moon settings work for that. So yeah, if you get out a nice telescope, you make yourself, grind your own lenses, get your own plastic tubes or whatever you want. You can use PVC and whatever, and do your calculations and your lens shapes and get something similar to this magnification. You're going to see this. And let me know when you're done with your experiment with your homemade telescope and see what results you get. If you see cities and technologies there, then I might believe you as far as whether the P900 or the telescopes are trying to fool us. I think, again, the burden of proof lies on those who make the charge that these things are monkeying with what we're seeing. And I don't think they are. But here again, that's not my point to prove, because I don't make that argument. I'm thinking they're legit. As far as a major telescope like the Los Alamos or the Lucifer or any of those big funded billion-dollar projects, they're probably seeing accurately, but they're not going to tell us what they're seeing. They're not going to show us the pictures, not without doctoring them. That's where the shenanigans come in, is when somebody says, this is a picture I took with my fancy billion-dollar taxpayer-funded telescope. Then you can say, yeah, you probably faked that. But when it's my own stuff that I took, no. So anyway, that's all I wanted to say today. I will add this to my cosmology playlist, but the point, once again, is we see evidence here in this picture of depth of field. The moon is not flat. And by the shadows on the mountain range and the indentations of the craters, we know that this is spherical, not concave. And that's all the point I wanted to make today. Thanks for watching. See y'all later if I can just find where the window is with the off button. There we go. See y'all later.